All right, so we are now in week 13. We're almost done with the course. In fact, if you think about it, we have today and Thursday of this week. We have Tuesday of next week, which is 3. We do not have Thursday of next week, which is Thanksgiving. And then we have Tuesday and Thursday of the last week, which is 5. And we only have 2 chapters to go, 11 and 24. Although 11 requires 6. So that might be in a day in itself, even though 6 is really, really easy. But we're going to start now on chapter 11. So what chapter 11 is dealing with is probability, okay, is likelihood of events. Now we've done some, we've covered a little bit the concept of probability, because throughout the course we've had questions like, is this outcome likely given the assumptions of the null hypothesis, for example? If the null hypothesis is true, do we expect to have this outcome or that outcome, etc.? But what we want to do now is delve a little more into the details of probability. So we're going to start with the idea of what's called a random experiment. There are many situations in the real world, where you perform an experiment or something happens and you do not know in advance what the outcome is going to be, but you do know what the outcome might be. Can someone give me an example of something in real life where you don't know in advance what the outcome is going to be, but you do know what it might be? I'll give you one example, and then you give me a few others. So an example that I'll give you is going to be flipping a coin. If you flip a coin, do you know in advance what you're going to get? The election. Okay, there you go. The election. That's a great one. We know that there's essentially 2 possibilities for the election, right? It's going to be either Trump or it's going to be Biden. A dice roll, another situation, right? You know it's going to be either a 1, 2, 3, 4, 5, or 6, but we don't know which number it's going to be. Having a boy or girl, right? It's going to be one or the other. Sports games, right? Someone's going to win. Maybe they'll tie. I know in hockey, I think you can have ties. Soccer, you can certainly have ties, I think. You're not going to really have ties in most other, sports, but you can, right? So all these things have certain things in common. What are those things that they have in common? One, you know the listing of all possible outcomes, even if you don't know what it's actually going to be. Does the chapter have a lot of math? The chapter, yeah, it has a little bit of math. I won't say a lot of math, but certainly it has a little bit of math. Anyways, back on track. So when we do a experiment like this, okay, all of these things have the same thing in common. You don't know in advance what the outcome is going to be, but you know the possibilities. We call those random experiments. Now, you don't literally have to do it yourself for it to be a random experiment. Like if I'm curious, is it going to rain today on my house? Because it's going to rain somewhere, obviously. If I'm asking, is it going to rain today on my house? That's a random experiment, because it's either going to rain or not rain. It's going to be one or the other. I just don't know which yet. Okay. So when you have a random experiment, the sample space is the collection of all possible outcomes. The sample space is the collection of all possible outcomes. So for example, if I flip a coin, what's my sample space?
Heads or tails.
Heads or tails. Not 50-50, right? 50-50 is the likelihood of getting to those. The sample space itself are the outcomes, heads or tails. If I have a child, what's the sample space? And let's just go biological and not worry about anomalies. So if I have a child, what's the possible outcomes?
Boy and girl.
Boy and girl, that's the sample space. The election, Biden or Trump, or I guess technically there's a few others it could be in theory, right? Aren't there other like 1%ers, if that, on the ticket? I don't know. I don't know politics, but you know, Kanye, Kanye. Yes, exactly, like Kanye, right? Um, so in general, the sample space is the collection of all outcomes. Now, an event is a collection of outcomes. So, for example, if I if I roll a die, how many outcomes are there? There's six outcomes, right? 1, 2, 3, 4, 5, or 6. If I say I want to get an odd number, so an odd number is not an outcome, right? Being odd is not an outcome. The outcomes are 1, 2, 3, 4, 5, and 6. But getting an odd number is an event. It's a collection of outcomes. It's a collection of 3 outcomes, a 1, a 3, and a 5. That is the event, getting an odd. Okay. Um, if I if I roll 2 dice, okay, dice are great examples because they're so you know ingrained in us. At least with me, growing up, played a lot of dice games. If I roll 2 dice, how many outcomes are there? Not let's put it this way. If you roll 2 dice, how many possibilities? Okay, so you have the answer. There's 36 outcomes, right? The first die could be 1 through 6. The second die could be 1 through 6. So it could be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 2. You go through all of them. There's 36 possible outcomes. If I say I want to get an 11, then that's an event because getting an 11 comprises the outcomes 5, 6 and the outcomes 6, 5. It's a collection of outcomes. Okay. A probability model is a sample space together with probabilities for each outcome where, so again, a probability model is I don't even know what I wrote anymore. Someone read it for me. What's a probability model?
A sample space together with with probabilities for each outcome where.
Okay, so there's 2 conditions that must be satisfied for it to be a valid probability model. Condition number 1 is that each probability must be greater than or equal to 0. You can't have a negative likelihood of an event, right? That makes no sense, right? You can't say, oh yeah, the chance of this happening is negative 0.3 or something like that. That makes absolutely no sense, correct? You guys with me? Yes, no, maybe so?
Yes.
Okay, and the other one is that if I add up all the probabilities, what must it add to? What do you think if I add up all the probabilities that it would add to?
100%.
100%. And the probabilities must add to 1. So let's write out, well, 100 you say, but it's really 100%, right? Correct? It's really 100%. Do you agree? Yes? No? Maybe so? Yes. Okay. So let's come up with a probability model for rolling a die. What is the most obvious and natural probability model when it comes to rolling a die? Remember, we have to look at the sample space and we have to assign a probability to each outcome. So,
Professor, may I see your paper one more time?
Yeah, of course. I'm sorry.
Thank you.
You're welcome. Yeah, die bug. Sorry. So when it comes to rolling a die, what is the most straightforward probability distribution that I can give to each outcome for rolling a die? How likely should each event be? Anyone?
1/6.
1/6. Doesn't that seem the most reasonable? That there's a 1/6 chance for each one? Now, if it's a weighted die, would that still be 1/6?
No, because if it's weighted, some other number has a greater chance of being.
Exactly. So as long as the numbers add to 1 and they're all greater than or equal to 0, it is a valid probability model. It might not be the correct one, but it's valid in the sense that it's theoretically correct. So for boys and girls, I'm having a child. It could be a boy or it could be a girl. What is a valid probability model for that situation where there's 2 outcomes? What is a valid probability model? 50-50. Is it accurate? Is it actually 50-50? So the answer is no. Boys are actually slightly more common than girls. And what I've read, which may or may not be correct, is that that was a response to an evolutionary model where boys have a higher mortality rate when they're younger, and therefore they need more boys to even it out. I don't know if that's true or not because that's not my field, but that's what I've heard. Anyway, this is the 3 first definitions: sample space, event, and a probability model. Okay. Now let's write out some rules of probability. These rules must be satisfied. Rules of probability. Rule number 1. All probabilities must be between what 2 numbers? So yeah, so Sydney, in that case, a probability model would be 50-50, 1/2, 1/2. 0.5 for boy, 0.5 for girl. It might not be accurate, but okay, good, Kiana. All probabilities, all likelihoods must be between 0 and 1. What does 0 represent as a probability? What does 0 represent as a probability? Yeah, but what does it represent? Well, 0 is 0%, I know, but what does it represent as a probability?
Like an impossible outcome.
An impossible outcome. Okay, an impossible outcome. What does 1 represent as a probability? What is 1? All of 1 outcome? I'm not sure what you mean by that. I'm not sure what always will happen. A certain outcome. Excellent. So 0 is something which is impossible. And 1 is something which is certain. Okay. Most actual probabilities are, of course, going to be somewhere in between. Okay. Does that make sense so far? So that's rule number 1. Rule number 2. If you add up all the probabilities, well, I already said this, so I'm not even going to write this as a rule because I already mentioned it. But the probabilities have to add to 100%. I've already mentioned that. Okay. So rule number 2. If A and B have no overlap. So if A and B have no overlap, what does that mean? A and B have no overlap.
That means like if the probability of 2 things happening, they both can't be 60%.
Well,
Right,
we're not going to the math yet. We're just talking about the overlap itself. What does it mean that
the probability of 2 things happening at once?
I'm not sure what you mean by that.
Like, is overlap like if you were to roll a dice and it land on 2 numbers at the same time, even though it's not possible? I know it's a bad example, but
okay, no, that's fine. So that's perfectly fine. An overlap could be rolling a 1 and rolling a 2. or no overlap, right? Rolling a 1 and rolling a 2. They can't overlap. You cannot have both of them occur at the same time, right? A and B have no overlap. A is rolling a 1, B is rolling a 2, there's no overlap. What's something else with no overlap that's a little more,
Like you can't have a boy and a girl at the same time unless
okay,
they're twins.
you can't have a boy and a girl at the same time. I mean, again, we're going into the standard, you cannot have a boy or girl at the same time. Could you have a prime number and an even number if you roll a die? If one event is rolling a prime and one event is rolling an even, is there any overlap to those? Yes, 2. 2 is both, right? So there is an overlap in that case. So no overlap means you have two things which cannot both occur at the same time. Okay, that's what no overlap means. Does that make sense? Yes, no, maybe so?
Yeah, that makes sense.
Okay. So if A and B have no overlap, if A and B have no overlap, then the probability of A or B is equal to what? It's equal to the probability of A plus the probability of B. If A and B have no overlap, then the probability of A or B, one or the other, is equal to the probability of A plus the probability of B. Does that make sense? Yes, no,
I'm a
maybe
little
so?
confused.
Okay. Suppose I have the following question. Let's say you roll 2. You ever play craps? Or hear of the game craps in
I've
Vegas?
heard of it.
Okay, so in craps, at one stage in craps, we might be interested in rolling a 7 or an 11. Okay, so suppose at one point we want to roll a 7 or an 11. Okay, so if I want to roll a 7 or 11, the question is, what is the probability of rolling a 7 or an 11? Okay, let's say I'm curious, what's the probability of rolling a 7 or an 11? How do I calculate the probability of rolling a 7 or an 11? Well, is rolling a 7 and 11, is there any overlap? Can you roll a 7 and 11 at the same time? You can?
All right, no, if you're just using one die.
No, 2 dice, right?
Two
2
dice,
dice. Okay, can you roll a 7 and an 11 simultaneously?
Yes.
Really? How can you roll a 7 and 11 at the same time?
No, 2 dice
Oh,
have to add up
wait.
to 11.
Oh my God, yeah. There's only 6. Okay, never mind.
Okay, so you can roll a 7, you can roll a 6, you can roll 2, you can roll a 9, you can roll an 11, but you can't roll a 7 and 11 at the same time. Okay, so if I say, what's the likelihood of rolling a 7 or an 11? Because there's no overlap, I can just calculate the likelihood of rolling a 7, calculate the likelihood of rolling an 11, and add them together. Because there's no overlap, I can just do them separately.
That makes sense. Thank you.
Okay, so that's if they have no overlap. If they do have an overlap, we'll get to that in a second. So the next rule, the third rule, the probability that A does not occur plus the probability that A does occur is equal to what? The probability that A does not occur plus the probability that A does occur is equal to what? It's equal to 1. It's 100%. It's got to be one or the other. Either A does occur or A does not occur, right? It's got to be one or the other. Correct? Yes, guys, I need some kind of acknowledgement here.
Yes.
Okay, otherwise I don't
Yes.
know. Okay, so there's no overlap, and it's got to be one or the other. So it has to add to 100%. These are the three basic rules of probability. Okay, these are the three basic rules of probability. Okay, now. Okay, so let's do an example. What is the probability of rolling a 5? Straight up. What is the probability of rolling a 5? You roll 2 dice, not one. You roll 2 dice. The question is, what is the probability of rolling a 5? So the first thing you want to ask yourself is, okay, well, how many outcomes are there when I roll 2 dice? Not the sum of 2 dice. One second. Not the sum of 2 dice, but the actual outcomes themselves. How many outcomes are there when you roll 2 dice? Mariah said it earlier. Anyone remember? How many outcomes are there if you roll 2 dice? 36. What you have to ask yourself is, of those 36 outcomes, how many of them will give a 5? How many of those 36 outcomes will give a 5? Anyone know? $12? There's 12 ways of getting a 5. What are those 12? List them all out for me. I'll give you the first one, a 1 and a 4. If I get a 1 on the first die and a 4 on the second die, that gives me a 5. 3 and a 2. That's 2 ways so far. 2 and a 3. That's 3 ways so far. I gave you 1 and 4, so you just repeated me, but thanks. You know, I appreciate it. Flattery is amazing. 4 and 1 is 4 ways so far. Are there any other ways of getting a 5? That's it. There's no other way of getting a 5. Which means 4 of the 36 possible outcomes give you a 5. Can we conclude immediately from that what the probability is, or do I need one more piece of information? Or is that enough? Anyone? Can I conclude from that, or do I need one more piece of information?
Do you need the probability of getting those numbers in case it's a weighted die or something?
Essentially, yes. Okay. If it's not a weighted die, if the dice are fair, then what's important to realize about this scenario is that all 36 of those are equally likely outcomes. That's why the answer is 4 out of 36. There's 36 outcomes, equally likely outcomes. 4 of them will give me the number that I'm looking for. And therefore, without reduction, without simplifying, the probability is straight up 4 out of 36, which of course is 2 out of 18, which then becomes 1 out of 9. Okay. Usually at the end of a problem, you simplify, and the problem is over technically. But in the middle of the problem, quite often what's going to happen is you're going to want to keep common denominators. So some are going to simplify and others won't simplify, and then the denominators are all going to be different, and then you're going to combine things together and it makes it harder. So as a general rule, I don't simplify till the end. But in general, there's nothing wrong with simplifying. Okay. Now, what's the probability of rolling a 3 or more? What's the probability of rolling a 3 or more? How do you get that? Well, first of all, it's not correct, but it's a good guess. But how do you get that? Did you actually go ahead and go through every possibility from 3 to 4 to 5 to 6, and so on, and check. to
In
make it work.
what I thought of was that like there's 2 possibilities of getting anything lower than a 3.
Yeah.
This is 136. There's 2.
Are there, what's the smallest number that you can get with 2 dice?
2?
2. So what are the 2 possibilities smaller than a 3?
So 1 and 2 and 2 and 1.
1 and 2 and 2 and 1. Okay, so you implicitly use the idea that I'm trying to establish, which is what's easier? Calculating every possibility for 3 or more, or calculating all of the other possibilities besides 3 or more, and then doing what to that number? Look at our 3 rules of probability, and particularly look at the 3rd rule of probability. What does the 3rd rule of probability say?
You add the probability of A not occurring plus the probability of A occurring, and this should equal to 1.
Okay, which means if I want the probability of something occurring, I can do 1 minus the probability that it does not occur. So if I want the probability of rolling a 3 or more, that's the same thing as 1 minus the probability of rolling what?
Can you move the paper up a little bit?
Yeah, sorry. If I want the probability of rolling a 3 or more, that's going to be 1 minus the probability of rolling what?
Probability of rolling 2?
Exactly, because rolling a 2 is the only way that you do not roll a 3 or more. Correct? Do we agree? Yes, no, maybe so? Yes? Anyone?
Got it.
Is it 2? Tell me, Ingrid, if I'm rolling 2 dice and I do not want a 3 or more, what am I going to get if I'm not going to get a 3 or more?
If you're not gonna get a 3 or more, what are you gonna get?
I ask you first.
I don't know.
Well, have you ever rolled 2 dice?
Yeah.
Okay. If you don't get a 3 or more and you have to get something, what do you get?
Either a 1 or a 2.
Well, you can't get a 1 if you roll 2 dice.
Oh. Oh, I see. I see.
Right?
Okay.
So the only way of getting not getting 3 or more is to get a 1 or a 2, right? I mean, it's to get a 2.
Yes, yes, I get it.
Okay, now the question is, what's the probability of rolling a 2? What's the probability of rolling a 2? How many ways can you roll a 2?
Are you still asking me?
Anyone? How many ways can you roll a 2?
1 time.
Not.
2?
So there's just, no, try again.
2 out of
Only
3.
one way of rolling a 2. What's the only way of rolling a 2?
1 on the first dice and then 2 on, no wait, 1 on the first and then 1 on the second.
1 on the first and then 1 on the second. Only one way.
Oh, I'm an idiot. Sorry.
I see.
So the answer is 35 over 36. Does that make sense? So, well, the probability of rolling a 2 is 1 out of 36. So the probability of rolling a 3 or more is 1 minus that, which is 35 over 36. Right? Yes? Yes? No, maybe so? Yes, okay.
Yes.
So, okay. Okay, so those are the basics of probability, and hopefully they make sense. What we're now going to do is talk about 2 different types of probability models. Oh, what's on the menu and who on the desk? Oh, the desk content. I actually haven't even thought about that. I've been so busy. So I haven't even looked at that yet. That's pretty funny though. And what's for dinner? It's probably some crap. I don't know. It's not gonna be good. Okay. So the two types of probability models are what are called discrete and continuous. Okay, discrete and continuous. Do you guys know the difference between discrete and continuous?
Is discrete like a full number or like okay, something like that? And then like continuous is like you could have decimals and stuff like it.
Okay, I love what you're saying. It's not 100% accurate, but I love what you're saying. Discrete in general means that the numbers can be separated, like 1, 2, 3, 4, 5. Those are all discrete because the numbers have a jump in between them. Continuous means that there's no jump in between them. So, like for example, if I'm curious, let's say you're shooting basketballs, and I say, okay, I want you to keep shooting until you hit 5 in a row. So if I'm curious how many shots it takes before you get there, then of course it can take 5 shots or 6 shots or 7 shots or 8 shots. That's a discrete model because the numbers, the possibilities in the sample space are all separated. But if I say how much does a person weigh, and I look at random people and how much they weigh, or how tall they are, or how much rain fell, well, it's true that our measuring devices are not accurate enough to get to the infinite decimal place. But from a realistic standpoint, those are continuous. There can be any number in between from one number to another. Those are all possibilities. And because any number in between can work, they're all possible. We call it a continuous model. Okay. And when it comes to math, the techniques that we use for the discrete case are different than the techniques that we use for the continuous case. And which one do you think is easier, the discrete or the continuous? Which one sounds easier? Let's put it that way. So discrete is in fact easier. To do continuous well actually requires calculus. And we do not have calculus at our disposal. So because we do not have calculus at our disposal, we can only kind of skim the surface on continuous. But we're going to do discrete a little more thoroughly. And in fact, all of the examples that we've done so far, if you think about it, all of the examples that we've done have actually been discrete. Because every example that we've done so far has been what? Anyone? Every example that we've done so far has been what? They've all been discrete. All the possibilities have been separated. The dice rolls are discrete. The boy or girl, of course, there's just not numbers, but it's discrete. It's boy or girl. Every example has been discrete, okay? Because there's much easier. For the discrete case, it's very straightforward. What we do for the discrete case is you list the possibilities and you list the probabilities of each, okay? Now, what's even easier than discrete is what is called finite. Finite means that, well, you tell me, what does finite mean? Anyone? What does finite mean? Someone say it out loud. What does finite mean? Anyone?
There's an end.
Sorry? What does it
There's
mean?
an end.
It doesn't end?
Finite means there's an
Finite means
does
there's an end. So give me an example of something that's finite. Limited. Okay, limited is a good word too. But limited is not 100% correct because it can still be continuous. That's something else. But give me an example of something that's finite.
Resources, fuel, gas.
No, okay. I don't mean finite in that sense, which is a real world situation. I mean, in terms of probability. Okay, boy or girl is finite. The universe again. That's a more of a non-probability type thing. Life expectancy in years is finite. I guess it can be anywhere from you were just born until, I don't know, 120, 130. Has there ever been a cap on that? I don't know. I mean, if you think about that, can a person live 120 years? In theory, can a person live 120 years? Probably not, but it's possible, right? So if it's possible, so the next question you want to ask yourself is, okay, if 120 is possible, is 121 possible? Can you go just a little bit further? And can you go just a little bit further? And can you go just a little bit further? Is there a point that you end? I know, yes, unlikely, I agree. I'm not arguing in any way with that. But the question is, can we consider the possibility as a possibility? If we can consider the possibility as a possibility and it goes on forever, then it's not finite. But we know that no one's gonna live a million years. So there's got to be some ends. So it is finite. We just don't quite know where that finite number is. But dice rolls are certainly finite. Coin flips are certainly finite. Problems with cards are certainly finite. How many, you pull cards out of a deck or something like that. We haven't really talked about that example. These are all finite situations. What's a continuous situation or a non-finite situation is the following. Let's say that you decide to, who here sucks at basketball? Like really, really is bad at basketball. Like is just, wow, this person's bad. Okay, Sydney, you're on point. Okay, Sydney, you suck at basketball. Here's what I want you to do, Sydney. I want you to stand at the half court line and shoot until you make a shot. That's what I want you to do. I want you to go to the half court line and shoot until you make a shot. How many shots do you think it'll take before you hit it? How many shots do you think it'll take before you hit it? 35? Okay, well, I think even good players might take 35 shots. I was trying to come up with an example where the answer can be like a gazillion. So maybe we'll go to full court. How's that? We'll do full court instead. Okay, and I want you to not only you have to make it from full court, you got to do it with your weak hands and it has to bounce twice. I don't know, something like that. Okay. The point is that in theory, it can take infinite amount of shots to take. Like there's no end where you can say this number is the last number and it can't be past that. That's an example of an infinite case. Okay. But even something like the following, let's say I flip a coin, something simple. I'm flipping a coin. And I say, I want you to flip the coin until you get a heads. So this is, a fair coin, 50-50, something simple like that. What's the probability that you get a heads on the very first flip? What's the probability that you get heads on the very first flip? 1 out of 2, 50-50, right? What's the probability that your first head is actually going to be on the second flip and not the first flip? No longer 50-50 because remember, for your first flip, for your first head to be in the second flip means that you must have missed the first one and then made the second one, right? You got a tails in the first and a heads in the second. What's the likelihood of getting a tails in the first one? $50-50. And what's the likelihood of getting a tails in the second one? Mariah's got it. It's actually a 1 in 4 chance because you got to miss the first one and then make the second one. And that is 50-50 for the first and also 50-50 for the second. And what if I say the first one's on the third flip? What's the likelihood that the first head's on the third flip and not the second, but the third one? not 16. Remember, it's 1/2, 1/2, 1/2. So what's the likelihood that the first head is in the third flip? 1 out of 8. How about on the fourth flip? 1 out of 16. How about the first flip? Or the fifth flip? Where did 1 and 20 come from? We had a pattern going there. Where did 1 and 20 come from? Just kidding. Okay, she's kidding. It's fine. Everyone take it back. She wasn't serious. It was all a joke. So we have 1/2, 1/4, 1/8, 1/16, 1/30. Oh, I just gave it. Oh. What's the probability of the first one and the fifth one? Anyone? I gave it away. I even started saying it. Nobody heard me? Or maybe no one's listening. That could be it too. No, not 1 out of 36. Not one. Ooh, Boat's here. Boat's here. Thank you.
Is it hot?
I got put them, but okay, good. 1 out of 32. Yes, it's 2 times 2 times 2 times 2 times 2. It's nothing. It's penne pasta. It's just this little bowl of pasta. It's so little. It's. They don't feed me on this diet. That's the problem. Anyways, the point of this is that in theory, the first heads could be on any flip up until a million. Right? The first one could be on any heads up until a million. So because of that, not just a million, a billion, a trillion, a gazillion, go on forever. Because of that, this is a not finite situation. For continuous models, well, actually, you know what? We've done a continuous model. Can anyone give me an example of a continuous model that we've actually used already in our class? Can anyone come up with the one that we've actually used in our class, a continuous model? Come on, you guys know what I'm talking about. What is it? What is it? Continuous model, you got this. Discrete can be finite or not finite. Discrete just means the numbers are separated. Think of the numbers from like 1 to infinity, 1, 2, 3, 4, 5, and so on. Are those numbers separated? 1, 2, 3, 4, 5, all the way to infinity. Are those numbers separated? But it's still discrete because they're still separated, right? Discrete just means separated. It could be finite, it could be not finite. That doesn't make a difference. Discrete just means separated. Okay. So can anyone think of a model that we've used in our class which is continuous, which has no gaps in it? Regression lines, it's something else. I'm talking about a probability model that we've used a lot this semester. A probability model that we've used a lot this semester. Normal distribution, fantastic. The normal curve is continuous, right? In theory, it could be any number from negative infinity to infinity. Of course, the ones near the middle are more likely. Of course, that's the whole point of the normal distribution. But in theory, it could be anything. That's a continuous distribution. So when it comes to a finite distribution, a finite probability model, you can actually say, what is the probability of getting a specific number? For continuous, you can't do that. We can't say for a normal distribution, what's the likelihood of getting exactly a 17? Because there's infinitely many possibilities. So 17 is so thin on the distribution table that the likelihood of getting it is essentially 0. If the likelihood of getting it is essentially 0, it makes no sense because it has to be something. So how can you say the likelihood of every event is going to be 0? That makes absolutely no sense. The only thing you can do for continuous is ranges. The likelihood of this number to that number. For finite, you can do each one individually. But for continuous, you can only do ranges of numbers. And we've done that this semester. We've certainly talked about that this semester of calculating, like for the normal distribution from -1 to 3, right? You do everything less than 3, and then everything less than -1, and you subtract. We've done this situation before, correct? This is not new, right? We all agree? Yes, no, maybe so? You all with me? Okay.
Yes.
So this is the basics of probability, and it is chapter 11. This, what we just did, is chapter 11. And the types of problems that you're going to see on chapter 11 are all problems similar to the things that we just did. You're not going to see anything more complicated. So let's go ahead and actually do some more complicated, not more complicated ones, but let's do some examples from the book just to show you that the kind of problems that you're going to have are exactly the same. So let's do the following problem. Let's see, we have a question here. Well, this one should be very familiar. So in the book on page 278 is a table of a probability model for political affiliations of a randomly chosen adult in the United States. And this is what it says. Republicans are 26%. Independents are 40%. And Democrats are 33%. Democrats are 33%. And other has a question mark by it. Other has a question mark by it. Why would other have a question mark by it? Because what they're saying is that they're not giving us that information and they want you to provide it. How can we use what we have so far, first of all, to figure out what the number is going to be for other? Again,
Because it has to add to 100.
Say again, what is it?
It has to add to 100 or 1.
It has to add to 100% or it has to add to 1. Exactly. So what number does it have to be? Yeah, 20. Yeah, here, I'll write it again. Do it again. Do you all see it? Okay, so what's it going to be? 40, 50, 70, 70, 90. Oh, that's easy. What is it going to be? What's the other? Anyone? What's the other going to be? Not, yes, exactly, 1%. It's got to add to 100%. It's got to add to 1. So the other three numbers already give us 0.99. And therefore the last one must be 0.01, which is 1%. Okay, excellent. Now, is this model continuous, finite, or is it even better, equally likely? Of course, in theory, it could be equally likely for any of them, but well, for finite, not continuous. Anyways, is it continuous? Is it finite, or is it equally likely? It is finite because there's 4 elements in the sample space. Because there's 4 elements in the sample space, it is finite. Next, what is the, oh, we already answered that one. So here's one. What is, huh?
Could you just repeat why was it again? It was 4 for finite. Was that a rule?
Well, no, there's 4 outcomes. It's Republican, Independent, Democrat, or other, right?
Yeah.
So that's certainly a finite number, right? Only 4 of them. That's certainly a finite number. Right? It's infinite. There's infinitely many possibilities, but there's only 4 possibilities. Right?
Wait, so finite is when it's not infinite.
Finite's when it's not infinite.
Okay.
Right? It's got to be one or the other, right? Finite's when it's not infinite. Okay. So what is the probability that a randomly chosen person is a member of one of the 2 major political parties? What are the 2 major political parties? Republican and Democrat, right? So what's the probability of the event's major political party? What is the probability of being in the event major political party? Well, it can't be two different answers, right? The event major political party can only have one answer. What is the probability of being in a major political party? Nope, they're not equally likely, so it's not going to be 25% each or anything like that. Look at the numbers that I gave you. Look at the numbers. What's the probability of being in a major political party? Well, the first thing you want to ask yourself is, so someone said 59%. And that is correct, because you have a 26% chance of being a Republican. You have a 33% chance of being a Democrat. There's no overlap between them, right? It's not, there's no overlap. It can't be both. And therefore, if I want one or the other, what's my rule that I told you? You just add them. 26 plus 33 is 59%. So the answer is going to be 0.59. That's why you add. Boom. What's the likelihood that a randomly chosen person is not a Republican? What's the likelihood that a randomly chosen person is not a Republican? $41? Is that 41%? Excellent. Can you tell you how you got 0.74? Can you explain how we got 0.74? Either Sydney or Mariah or Denitsa? Add everything except, okay, that's one way of doing it. And it looks like Sydney did the same thing, right? Add everything except for that one. Was there an easier way of doing it? Was there an yes, 1 minus 0.26. All right, 1 minus 0.26. Excellent. Excellent. So we've illustrated the 1 minus rule. If you use that one here, you didn't have to, because there's like 3 possibilities. So just add them up. But let's say it's 100 possibilities. Would you want to add up all the 100 or just say 1 minus that one? For 3, probably faster to go direct. But for 100, certainly it's faster the other way. So you want to, be aware of the others. You want to understand the overlap rule and how to add or possibilities. The concept of continuous, finite, equally likely, probability models having to add to 100%. This is chapter 11. How do you feel about it? Good. Was it one of the easier chapters, one of the harder chapters? Great. Wow, Mariah. It's logic, right? I love probability. Statistics is like, statistics is like, a different way of viewing things. But probability, I love probability. It's just very, very, once you get the rules down and you know how to apply the rules, very, very logical how to do it. Anyways, so I'm going to stop recording.